Today I'm actually going through a presentation. I'm not going live into Atlas. And the reason for preparing this presentation is actually the new functionality in the Mac version, which already exists for a long time in the Windows version as well. But now you can also look at the code forest and the code tree in the Mac version. And one frequent question, of course, is in Atlas, does Atlas have like a code hierarchy? Well, you can enforce a code hierarchy or a hierarchical structure for your code list using the code forest, but only in particular circumstances. And on the Atlas website, you also find two videos. One is more on the technical aspects, showing you the mouse clicks in the new Mac version, and then some methodological concerns in those videos are recorded by Ricardo. And I'm kind of doing a bit of more theoretical background now, in case you wondered what's behind semantic networks in ATLAS.ti. So I'm going to show you a bit of network theory, but only a little bit. I'm not going to going into the mathematics of it. And then I switch over at the end of the presentation to Atlas and show you what the network view function in Atlas can do and how you need to limit it, or how you limit it, depending on how you see it, if you use it as a code for a hierarchical structure of your code system. And if you know my work, you know how actually I'm organizing and structuring the code list to get a hierarchical structure without having to use the network view function, because the network view function can be used for so many more things. So here's just a definition of what is a semantic network. So semantic networks are knowledge representation schemes involving nodes and links, also called arcs and arrows between nodes. So you know the term nodes from Atlas, so all objects in a network view are nodes, and then we have the links, and then you can name the links. These are the Atlas relations, so everything that you see in that little image in yellow would be an Atlas relation. So the nodes represent objects, could be codes, memos, quotations, PDs, families, and so on, or concept, and the links represent relation between the nodes. So in Atlas, as it is currently, you can link all of these objects I have just been mentioning, but you can only name these relations, the links with relations between two codes and two quotations. So these are the first class relations, or as Ricardo always refers to them as strong link relations and weak link relations for the others. I like first and second class. It's kind of a nice analogy in a sense as well, because of course the first class relations, they can tell you more than just being two objects being linked to each other. So we're going to stay a little bit with that kind of standard semantic network that you find also online. Sometimes the animals are exchanged with birds, but these are things that you find online. And I've always given the sources where you can find these, and at the in the description of the video I also give you the link to the presentation. It's a presentation, so you can actually view it online, and then maybe also zoom in and look at the sources I've been using here. So if we look at the terms here more closely, then we have higher and lower order terms, so sub or superordinate terms and subterms, and we also find a different terminology also in network theory. So the superordinate and the subterms here are bear, mammals, and animals. So animals being the highest order term, and then we have mammals as a subterm, and then below that we have bears or whales or fish, whatever, and the mammal is again the superordinate term for bear. We should call it bear. A bear is German. I think it's bear in English. So then you find also terms like hyperonyms, synsets that are more general for higher order, and hyponyms for synsets are more specifics. And there is a relation that you do find in Atlas, would basically be used to link a hyponym to hyperonym, so a superordinate term to a subterm. But then we also have other types of relation, things like meronyms. These are components or part of something, like the fur is part of a cat or a bear, or the other way to state it, it would be a bear has fur and a cat has fur. And now I'm already giving you some properties. Those relations are normally asymmetric. We'll talk about these properties in a bit. And also in the header here you see transitive and asymmetric relations, and I will kind of tease more apart what these are. Then we have synonyms. They express equivalence, like a handy could also be called a mobile phone or cell phone, depending on where you are. Well, in Germany we use handy, but that's not used in the English-speaking world, even though that's kind of an Anglicism we use. But it's the same as mobile phone or a cell phone. So such relations are reflexive, symmetric, and transitive. So reflexive because they kind of refer to each other. And let's leave these explanation for symmetric and transitive also for later on. And then we have antonyms. They express opposites. So that's also something, all these things that you can express using a network view function, not only higher and lower order terms. So you can already start seeing the difference between just using it as a code hierarchy, or for expressing things that are part of, or synonyms or antonyms, things are the opposite. Now, if A happens, then B happens, but if the opposite event happens, C, then actually D happens, and so on. So you can tell all kinds of stories with the network view function. And then we also have different type of relation properties. If you're familiar with Atlas, then you know we have symmetric relationship, asymmetric relationships, and transitive relationships. And there's no reflexive relationships, and we see that in network theory we have further properties that I'm not going to touch on. Then there's two more relations you might be using, causation and also a property of something. So if you want to take a closer look at this little cartoon here, it kind of refers to something you may have learned somewhere along the way, that an association is not necessarily a causation, and the difference between two things that are just related to each other and things that caused each other. So a causal relation in generally is a transitive relation and is not symmetric. And if you have something like these things are linked to each other and you cannot determine a cause, we would have a symmetric relationship, and that's why causations are not symmetric relationships. So you probably have read it in the meantime. Causation relates terms like events or condition. One event causes another, like an action of a particular person being late causes another person to become nervous or angry. So things like that you may express, and you have in your data that you want to express by linking your concepts. And a property of something is describing something in more detail. So something is very soft. It is light or strong or weak, whatever. So a nice term, it connects predicates with objects that are within the range of values of these predicates. So that would be the official definition. So that's something related to just one particular concept you have. And of course you could organize that into something higher and lower order if you want, But to express it more more correctly, in a sense, it would be an asymmetric relationship. And also, if you look at the is property relation of in Atlas, is an asymmetric relation. Wait a second until I get to the difference between asymmetric and transitive. Just to already kind of evoke that, in order to create a hierarchical code structure in Atlas, you only need to use transitive relations. So if you properly want to express a property of something, would be asymmetric, would already not force a hierarchy in Atlas. If you're interested in, I'm not going to click on this now, but as you have access to the presentation, if you're interested, look at this YouTube video. It explains in 10 minutes all of these different properties of relations. I have them in here in the presentation as well, and you will see that I'm going to skip them in the presentation. If you want a quick overview, I'll look at it at your own time. So the three here you have in dark red, these are the three properties that we have actually in Atlas. So let's take a closer look now of what these actually mean. So semantic relationships, in a more mathematical definition, a relation X is symmetric if it holds for all A and B related with X, that A is related to B, if and only if, we find this all the time, B is related to A. So I think the easier explanation is if just the graphic image of it here. The example of friends, Anne is friends with Tim and Tim is friends with Paul. That doesn't necessarily mean Paul is friends with Anne. So we don't have a transitive relation here, because then it would kind of go all the hierarchy down in a sense. But so it's a mutual relationship between Anna and Tim and Paul, and more correctly we would have two arrows going. Atlas is showing one arrow with one line with two arrows at the end, and not two lines. Yeah, so examples would be as shown in the graphic. Our friends is married to, in most legal systems, is a fully biological sibling of, or is a homophone of. So just to get you an idea of what you could link in terms of a symmetric relation. So going to the X and B thing shortly again, A is related to B if and only if B is related to A. X is always representing the relation here. It could be A is friend of B, or A is associated with B, and only if B is also associated with A. So it's mutually, they kind of refer to each other. So now let's move on to transitive relation. And here the more formal definition is if A has a relation X to B and B has a relation X to C, then A also has a relation X to B. This is also illustrated here by the image. So if I is linked with a transitive relation to B and then B to C, then also A is related to C. And then here this is also extended to D and E. That also mean B, the relation will also hold between B and E, between A and E, and also between A and D, and also B and D. So if we go to the examples, and we had the smartphone and the cell phone example before. So equality is a transitive relation. A equals B and B equals C, then also A equals C, if that's transitive. Is descendant of, also is transitive relationship. So if Peter is the son of Karl, and then Klaus is also son of Peter, then these are descendant of. So we couldn't use is son of, because son would not be transitive, because Karl had Karl as C, yeah? would not be the son of the grandfather. Yeah, so depending on the type of relation and also the name you're using, it works as being a transitive relation or not. But descendant of works because it kind of goes all the way back or through the family tree. Less than is a transitive relation because if A is less than B and B is also less than C, then A is also less than C. So mother or father or son or daughter is not a transitive relation because it would not inherit all the way through unless we have a special situation like Oedipus. Yeah, then it would also apply, just in case you've got Oedipus, is the also kind of a synonym for the mother complex because he married his mother, and then in case of one of the children they then had, it would apply that the mother was the mother of Oedipus, but also of her grandchild in a sense as well. But these are special situations. Sister, if you only have a group of females, is a transitive relation, as well as brothers, but only if we have a group of males, because Anna is a sister of Carla and Carla is a sister of Susanna, then also Susanna is a sister of Carla and Anna. Yeah, the same would hold for brothers. But if Anna is sister of Carla and Carla is sister of Paul, we don't have transitive relation because Paul is not a sister of Anna because he's a brother of. Yeah, so always depending also on the context and in a research sense you sample, sometimes the same relation name could be a transitive or an asymmetric one. So in the case of we have males and females in our sample and we use brother and sister, the property would be asymmetric because it's not going to be, you cannot kind of refer back. So what you see here in blue, I'm not going to go through, but you see also there's intransitive relations and there's non-transitive relations, and they will kind of defined in a bit of a different way. But as they don't apply to Atlas, I skip them here. So I already mentioned asymmetric relations here. We do have here a family tree, and if we use is descendant of, well, it would be transitive, but if we would use is child of, then you need to use an asymmetric relationship. So if X has a relation R to Y, but Y doesn't have a relation R to X, so if it is not going both ways, like in the example here, if Nick is a child of Mary, then Mary cannot be the child of Nick. In that instance, you have to use an asymmetric property, not the transitive one, if you want to do it correctly. So here we have the example of is less than again as being an asymmetric relation. And before I said it's transitive. So we can also impose something is asymmetric and transitive. So you can also have a combination of both. So it's really what you look at. So because if you look at only two elements, if X is less than Y, then Y is not less than X. So we don't have, it cannot go kind of backwards. But if you have X and Y and that, and X is smaller than Y and Y is smaller than that, then Z, then of course X is also smaller than that. So we had it with ABC before. So we have that also as in a mathematical sense also. It is more complicated than it actually it may already look complicated, but it's even more complicated than that. And in addition to that, we have anti-symmetric and we have non-symmetric relations. Again, that's in blue there. If you're interested in it, you can look at it in your own time. But you see, we have all kinds of properties, and then we, on top of that, we have combination of these properties. So here we have this example of a relation being transitive and asymmetric, going back to our first example with the bear and the whale and the mammal and the animals. Yeah. if you go one way, the animal or the bear is a mammal and the mammal is the animal, in that sense it's transitive, but we cannot go the other way around. The relationship between animals and mammal is an asymmetric one, because not all animals are mammals, because we have also vertebrates and non-vertebrates, and so on. So an asymmetric relationship means a relationship is not reversible, so that's maybe also something you can remember. In that case, as I mentioned, the animals and the mammals. And here you also have the more mathematical terms. A relationship is transitive and asymmetric, and this means the properties of the superordinate are inherited to all subterms. If A leads to M and M leads to B, then also A leads to B. Like the A and M and B stands for animal, mammal, and bear. But it's not reversible, so we cannot kind of go the way up. So it is transitive and asymmetric. So in a sense, you could also use it for a family tree, that downwards this is son of and son of and son of, but upwards it's asymmetric and not transitive. In ATLAS, you have to decide one way or the other. You cannot give a relationship two properties, but in fact sometimes they even have three properties or potential properties. So here we have one. Going back to the synonyms and the antonyms here, we had this before, reflexive, and you see now here in the image what reflexive means, kind of referring back to itself, like the mobile phone and the cell phone and the handy. So the relationship is reflexive. X is a synonym of X, and it's symmetric, because if X is a synonym of Y and Y is a synonym of X, then they refer back and forth to each other, like the cell phone is a handy and a handy is a cell phone. So if you have two concepts here, and if you have three concepts, then it's also transitive. If X is a synonym of Y and Y is a synonym of Z, and X is also a synonym of that. So if you had cell phone, mobile phone, and handy, well, a mobile phone is a handy, a cell phone is also a handy, and then we have our transitive relations going here. Antonyms, they relate terms that express opposites. We had that before, and such relations are symmetric but not reflexive and transitive, because they don't reflect on each other. They refer to each other. Being that is not the same as being alike, so they're opposite. But you can say being that is not being alive, and alive is not being that. So we have the symmetric property going, but it's not transitive, because we can kind of go down from alive to being dead and being something else, and going the transitive route here. So you see, there are lots of different ways of expressing how things are related to each other. And now I want to go back to ATLAS. So we have a little preview here. It might not be the final one, but how it actually looks like in version 8, Windows version 8 of ATLAS.ti. And we have a number of new layout options here, and here I'm always then using the semantic layout, and depending on if I also have new codes and how I've related them, ATLAS will kind of construct my semantic layout here. So ATLAS has more to offer in the networks. At least we have 3, transitive, asymmetric, and symmetric relationship, than just being a representation of a hierarchical code system. But you can of course use it for that purpose. And now I come kind of back to that nice mathematical term, if and only if. In this case, you only use transitive relation. because only transitive relations enforce strict hierarchy, where you can go from A to B to Z. Yeah, if we want to have a hierarchy, is property of is already asymmetric. It's not going the way upwards again. So if you would use that, it would also has an effect on how your code tree and forest looks like. So what you can see on the left hand side here in the image does not represent a hierarchical code structure. It expresses the semantics of the story the analysis wants to say. And this is also what I'm usually explaining what the network function in Atlas is for. It explains parts of the story of your research. Most of the time you cannot explain everything in one network view because often it's not enough space on the screen, so you have partial networks that give answers to your research question, but you can express it in form of a story of relation between concepts and make it more visual now than just having text. But it's different from just describing your code system in a hierarchical manner. So these are two different analytical steps. First step is to describe your data by building your code system, and I usually would use prefixes to get the hierarchy in place, to get the descriptive level in place, and then use the network view function to tell my story. But in case you want to use it for a hierarchical structure, you will see what's going to happen. What do I have to do to these codes in order to turn that into a hierarchical structure? So this is the structure. Apart from the red codes in the middle, I will say a few words about those. Of the network image you have seen before, like I said, this is just a story somebody wants to tell, but it's not organized in a hierarchical manner. Because what you see here, we have animal, fish, and then mammal, and then we have the three mammals here, but they also occur again here under vertebra, because the vertebra has been linked with has relationship which is defined as an asymmetric one here, and only the SA ones are defined as transitive ones. And the fish lives in water, but water doesn't live in fish, so we cannot use a transitive relation here either. The red one here is a symmetric relation, and with symmetric relation things refer to each other. So full is an antonym of empty, and M is an antonym of full. So we use contradicts with a symmetric relation, and they refer to each other. And this is also visible in your code tree or code forest. It stops apparently here not yet, but normally it stops after two repetition, because it would kind of refer to each other endlessly. Yeah, you can have a very long tree here. But you see the effect of the different properties if you're not only using transitive relations. So then what I was trying to restructure the code system, giving it a hierarchical touch, I also felt it was necessary to introduce other codes. And if I had the has vertebra wasn't really working, so I was looking at the animal system here and how they have described their animal kingdom here, the biologist, and so it's not complete here, but just to give you an idea, so they distinguish between invertebrates and vertebrates, and I think there's other ones as well, and then within those we can distinguish between flatworms and mollusks and arthropods and annelids. I'm not sure whether I pronounce this correctly now, but you see, if we now think in a hierarchical structure, we think in terms of systems. Yeah, and then we have animals, and we can divide animals into invertebrates and vertebrates and maybe other things. They are mammals, and then we can have under the mammals we can have the type of animals that fit underneath, and then the animals can actually it was the fur, so then I added fin and feather, and I couldn't leave it at has because otherwise it wouldn't show up on my tree, because if I use the code's tree structure for coding, maybe I want to have the animal skin kind of on the first level and it's not somewhere as asymmetric. So I do left the asymmetric relation here. So we have then the habitat. We only had water before, but then of course if you think in systematic ways, you also then have land and air and maybe other habitats. So it does of course give you other ideas, but if you see a hierarchical coding system in that sense, you often also have subcodes that are not coded, because also people thought about something in a more systematic way. It is not in the data, so it just stays empty, which of course sometimes also an important information. But here we had now animals that are did I add another one? Maybe I did one for air and land and water, which was the fish, and the cat and the bear are here. And if these are now not linked in a transitive manner, so you could open up the tree, but then you would have here again the repetition, because of course the bear and the cat would occur here again. But you can of course also not open up the tree fully and only leave it on your first, second level of hierarchy here. But you see what's happening. So you can of course combine it with asymmetric relationships, but then for the coding structure you can just leave that part of the tree closed. In a network view or network, I have to change my terminology here because we're gonna get rid of the view part and just calling it networks. It will look like that. So we have the animal here, and the animal is divided into invertebrates, and then I gave them all the same color, and invertebrates, so they're all lilac. And then the animals, the kind of type of animals that belong to a particular group, I gave them the pink color and the properties of what they have, so the animal skin, and they're blue. And I added a bird here, so to have an animal here for the air, for the habitat. So all habitats are blue, and then the fish and the bird. So again, in terms of colors, I might have would have changed them into pink as well, to have my hierarchical system here in order. So you see there's all kinds of changes then you start to make in order to get it into a more systematic way, and also start to change around color, because suddenly things shape up in a different way. So you can do it. You see the effects, and maybe I go back to the other view here that was more telling a story, because it had fewer codes now here as well, but maybe all the others didn't occur in the data. And if I think in a hierarchical way, I add them to my system, but it's not really in the data, and they just have then empty codes, so 0 quotations. So I hope this video has shown you the difference between a hierarchical coding system when using the network view function, and I usually would not leave the codes like that because they are not sorted in alphabetic order by their group. So to say, I would use prefixes in order to get a descriptive code system going, but then use the network view function to tell the story. But depending on your approach, you might have a very deductive approach. It might be useful to set it up like that, and maybe you also have data for all of these subcodes. But just be aware that you're then only utilizing part of the network view function, and also, and that's why I usually advise against doing this, it makes it difficult later on to use a network view function for telling you stories, for more conceptual work, because then your transitive relations are all in the way. Or you save your project after coding under a different name, and then start building your network in your conceptual networks in a copy of the project, and not thinking about getting rid of the transitive order you needed to have here to have your hierarchical code system in place. So you can do both, and depending on the nature of your research project, you may find it useful, and I hope I have enlightened you a bit about the add-on function of what else you can do with networks. Goodbye.